Hello everyone, my name is Abhishek Pandey. I'm a Prime Minister Research Fellow in the discipline of Mathematics at IIT Bhubaneswar. Today we are going to start with week 0 assignment. So let us start. Let us look at the first question. So it is asking which of the following statements are true under the usual topology in R2. So the given domain is first option, x comma y belongs to R2 such that y is greater than 1 and less than 2. So we need to check whether it is open in R2 or not. So this shaded region is the set omega. To check whether it is open or not, we need to check that for each point there exists a neighborhood which is completely contained in the set omega. Okay, so take any point x naught comma y naught belongs to omega. So here y naught is greater than 1 and less than 2, and let epsilon equals to minimum of mod of y naught minus 1 comma mod of y naught minus 2, and consider this neighborhood. So this is basically a circle, inside part of the circle. So first we will consider the circle center at x naught comma y naught and radius epsilon by 2. Okay, so this gives us that mod of y minus y naught is less than epsilon by 2. This implied y belongs to y naught minus epsilon by 2 comma y naught plus epsilon by 2. And since the way we have chosen epsilon, this will be completely contained in 1 comma 2. Okay, in the open interval 1 comma 2. Thus y is less than 2 and greater than 1. This gives that the neighborhood is completely contained in omega and hence omega is open. So the option 1 is true. Okay, now let us look at the second option. Here the set omega is nothing but x comma y belongs to R2 such that x plus y is greater than 1 and less than equals to 3. So if you take any point x comma y belongs to the line x plus y equals to 3, if you take any point on this line, say on this line, take any point, okay, and if you want to make a neighborhood, any small neighborhood, take any point, any other point. So every small neighborhood will have some part outside this line. Okay, this part. Okay, this part. So any neighborhood will not be completely contained in this set. Okay, so this set is not open. Okay. Now let us look at the third option. Third option is the same, and we need to check whether it is closed or not. Okay. So for the closeness, as we know, if the set is closed, if and only if it is equal to its closure. Now let us look at the closure of the set. So the closure of this set is nothing but x plus y is greater than equals to 1 and less than equals to 3. Okay, this one, which is not equals to omega. Thus omega is not closed. Okay. Now consider the next option. So consider this set. Okay, x square plus y square equals to 10. So now consider the function. Basically, we are going to use that under a continuous function. Inverse image of every closed set is closed set. Okay. So consider the function f of x comma y equals to x square plus y square. Clearly, this function is continuous. So the pre-image of any closed set is closed set. Consider the pre-image of singleton 10. As singleton 10 is closed set, so its pre-image also a closed set. And this pre-image is nothing but the set omega in R2. Thus, omega is closed set in R2. Now consider the set omega equals to x comma y belongs to R2 such that x square plus 2y square is greater than equals to 3. Okay. Now similarly consider the function f of x comma y equals to x square plus 2y square, and consider the pre-image of 3 comma infinity, closed interval 3 comma infinity. Okay, so since closed interval 3 comma infinity is closed in R, this is closed in R, therefore its inverse image is also closed in R2. So option 5 is true. Okay, let us look at the question number 2. So this is basically on sequence and series of functions. Okay, so let f n x equals to x to the power n and g n x is equals to x upon 2 to the power n. Okay, x belongs to 0 comma 1. So fx is equals to limit n tends to infinity f n x is equals to 0 when x is in between, x is greater than equals to 0 and less than 1, and 1 when x is equals to 1. Okay, since f is not continuous at x equals to 1, and as each fn is continuous, so fn does not converges uniformly on 0 1. So option 1 is true. So fn does not converges uniformly on 0, 1. So option 1 is true. Now let us look at this limit. Limit n tends to infinity integral 0 to 1 fn x dx is equals to limit n tends to infinity integral 0 to 1 x n dx, x to the power n dx. This limit will be limit n tends to infinity 1 upon n plus 1 equals to 0. And integral 0 to 1 limit n tends to infinity fn x dx is equals to integral 0 to 1 0 dx. So this will be 0. So here we have used the following theorem. So this theorem says that let f says that ab to r and phi says that ab to r be two bounded function such that fx equals to phi x except for finitely many points in a comma b. If f is integrable on ab, then phi is also integrable on ab, and the integral is same. Okay. Now let us look at the third option. Let hn x is equals to sine 2 pi x into fn x. X belongs to 0, 1. So hn x is equals to sine 2 pi x into x to the power n. Clearly hn x converges pointwise to hx equals to 0 for each point x belongs to 0, we need to check whether hn converges uniformly to hn. So for that we will use mn test. So let mn is equals to supremum of x belongs to 0, 1 mod of x to the power n sine 2 pi x. So at x equals to 0 and x equals to 1, this is basically 0. Okay. Thus it cannot attain supremum at x comma 0 and 1. Let it attains maximum at x equals to alpha. So mn will be alpha to the power n sine 2 pi alpha. Okay. So as n goes to infinity, mn goes to 0. Thus hn converges uniformly to hx equals to 0. Fine. Now let's just look at the fourth option. So gnx is equals to x by 2 to the power n, where x belongs to minus 2 to 2. At x equals to minus 2, gnx equals to minus 1 to the power n, which is not convergent. Thus gn does not converges pointwise on minus 2 comma 2 and hence not uniformly. If x belongs to minus 1 comma 1, x by 2 to the power n tends to 0 as n tends to infinity for each n. Okay, this one is quite clear. So thus gn converges to 0 pointwise on minus 1 comma 1. So again to check uniform convergence we will use mn test. So let mn is equals to supremum of gnx minus 0 on minus 1 comma 1. So mn will be of this form 1 upon 2 to the power n, and this goes to 0 as n tends to infinity. Hence gn converges uniformly on minus 1 comma 1. Therefore option D is correct. Let us look at the option E. So consider the series summation 0 gnx n goes to 0 to infinity, n goes from 0 to infinity. So summation n equals to 0 to infinity x upon 2 to the power n. So at x equals to 2, this is nothing but the summation 1 from n equals to 0 to infinity, which diverges. Okay, thus this option is false. Let us look at the option F. So summation n equals to 0 to infinity fn x upon n factorial is basically summation n equals 0 to infinity x to the power n upon n factorial. So we will use Weierstrass test. Consider any interval of the form a comma b and set m is equals to maximum of mod a comma mod b. Then modulus of x to the power n upon n factorial is basically less than m to the power n upon n factorial, which is this is your mn. Now this summation mn, we have to check whether this summation mn converges or not. So we will use ratio test, and using ratio test we will get that this summation will converge, and hence summation fn x upon n factorial converges uniform on every interval of the form this. So this statement is true. Now consider the third option, third question. So it is basically based upon the linear transformation, R linear map and C linear map. So first option is, so the linear transformation is defined as this. We need to check the first option. So t of x comma y equals to 0 comma 0 gives x plus 2y and minus 2x plus y equals to 0. So this is possible if and only if x comma y is equals to 0. So we have only one choice, which is 0 comma 0. Thus option 1 is not correct. Okay. Now let us check whether it is R linear or not. Okay. So for alpha belongs to R and x comma y belongs to R2, we need to check t of x plus y equals to t of x plus t of y. After some calculation, we get that t of x plus y equals to t of x plus t of y. And t of alpha x plus y is nothing but t of alpha x comma alpha y, and after doing calculation, we will get t of alpha into t of x comma y. Thus, t is R linear. Now, third question is before going to consider third option, let us recall some fact. Okay. So, as we know that the complex plane C is vector space over R as well as over C, so we can distinguish between R linear map and C linear map. So, a map T such that C to C is said to be R linear if T is linear map when we are considering C as a vector space over R. Okay. And a map T such that C to C is said to be C linear when it is linear map when we are considering C as a vector space over C. Okay, and this is the theorem. One can easily prove it that a map T such that C to C is R linear if and only if it is of the form AZ plus BZ bar. And similarly, a map T such that C to C is C linear if and only if it is of the form TZ is equals to lambda Z. Okay, so this gives the following corollary: every C linear map is R linear map. So let us look at the third option. So T of x plus iy is defined as this. So once we write in terms of z, we will get T of z is equals to 1 minus 2yz, which is of the form lambda z. Thus T is C linear. For the option D, see the corollary. Every C linear map is R linear. Now to check whether every R linear map is C linear or not, we will give a counter example. So let Tz equals to Z bar. This map is R linear but not C linear. Okay. Now consider the fourth option. It is regarding the function of several variable, basically two variable. So let the given function is f of x comma y equals to x into y upon x square plus y square if x comma y is non-zero and 0 if x comma y equals to 0. So let us check at the partial derivative with respect to x at the point 0 comma 0. This we will get 0. And the partial derivative with respect to y at the point 0 comma 0 we will get again 0. Okay, so both exists. Partial derivative with respect to x at any point is this. Okay, so now we have to check whether it is continuous or not. Okay, so let y equals to 2x and check the limit as x goes to 0. So we will get limit x tends to 26 upon 25x, which does not exist. Okay, so it is not continuous. Now for option D, take y equals to mx in fxy. So limit x tends to 0, mx square upon 1 plus m square into x square. This will depend upon m, which depends upon m. Okay, thus f is not continuous at 0 comma 0. Now let us look at the last option. Since f is not continuous at 0 comma 0, therefore it is not differentiable at 0 comma 0. So this is also done. Let us look at the fifth question. If fx is equals to integral 0 to x t p square plus sin t dt, then f dash x is equals to x square plus sin x. So recall that let f such that ab to r be a Riemann integrable function, and for x belongs to ab, define a function this. Then f has the following properties. Capital F is continuous on AB, capital F is differentiable at all those points where small f is continuous, and basically the derivative at x is equals to f of x at those points. Okay, so this is known as the fundamental theorem. Now here fx is equals to x square plus sin x, which is continuous on R. Therefore, capital F dash x is equals to small fx. Okay, so this is done. Now let us look at the option B. So f of x is equals to limit n tends to infinity fn x. Okay, where so fx will be 0 or 1 if x is greater than 0 and less than 1, and x equals to 1 when at x equals to 1 f of x equals to 1. Here fn x is equals to x to the power n. Define capital Fx is equals to integral 0 to x ft dt equals to 0. Okay, So for all x belongs to 0 comma 1, this integral will be 0. Okay, so capital F of x is equals to 0 for all x, so its derivative will be 0 for all x, but derivative at 1 is not equals to f of 1. Okay, so option B is not true. Now let us look at the option C. So define f such that 0 comma 2 to r by fx is equals to greatest integer less than x. So fx is equals to, so this will give, so greatest integer less than x means we have to find the greatest integer which is less than x. Okay, so suppose you are taking 0.7, so greatest integer which is less than 0.7 is 0. You are taking 1.2, so greatest integer which is less than 1.2 is nothing but 1. Okay, so now this function will be this. Define capital F of x is equals to integral 0 to x ft dt. If x is less than 1, integral 0 to x ft dt equals to 0. If x equals to 1, integral 0 to 1 ft dt is equals to 0. Okay. If x is greater than 1 and less than 2, then this integral 0 to x ft dt equals to integral 0 to 1 ft dt plus 1 to x ft dt. So we have to split the integral in two parts. So this will give 0 plus integral 1 to x dt. This will be equals to x minus 1. If x is equals to 2, then the integral is same, integral 0 to 2, so we have to split in two parts, integral 0 to 1 and integral 1 to 2. So this will be equals to 0 plus 1 equals to 1. Okay. So our capital X, so our capital F will be of the final form this 0 and x minus 1, 0 when x is greater than equals to 0 and less than equals to 1, and x minus 1 when x is greater than 1 and less than equals to 2. Hence capital F is not differentiable at x equals to 1. Okay, because by the graph you can see at x equals to 1 it is not differentiable. Okay. Now let us look at the option D. Let u is equals to 0 comma 1 union 2 comma 3. Capital of f of x is equals to 0 when x belongs to 0 1 and 1 when x belongs to 2 comma 3. So capital F dash x equals to 0 for all x belongs to u, but capital F is not constant. So for this statement to be true, u should be open and connected. Okay, so connectedness is also an essential condition for this statement to be true. Okay. Now let us look at the last question. So it is regarding the Taylor series of the function and differentiability. So given the function fx is equals to e to the power minus 1 by x square when x is non-zero and 0 when x is equals to 0. To check the differentiability x equals to 0, we need to check whether this limit exists or not. So limit x tends to 0, e to the power minus 1 by x square minus 0 upon x minus 0 equals to limit x tends to 0, e to the power minus 1 by x square upon x. So take 1 by x equals to h. So limit h tends to infinity, h e to the power minus h square is equals to limit h tends to infinity, h upon e to the power h square, which is of the form infinity by infinity form. Okay. Thus by L'Hopital rule, limit h tends to infinity, 1 upon 2h e to the power h square is equals to 0 exists. So f is differentiable at x equals to 0. Now option C is expansion of e to the power minus 1 by x square. So option C is, given a point x belongs to R, the Taylor series of f exists at x and is convergent to fx. So for every point x belongs to R, the expansion of e to the power minus 1 by x square is this when x equals to not equals to 0, and when x equals to 0 it is this. So it converges to f of x. Okay. So option C is true. For option D, we need to check the Taylor series of f around 0. So the form of the Taylor series is this: f of x is equals to summation fn 0 upon n factorial into x to the power n in some small neighborhood of 0. One can check that nth derivative of f at 0 equals to 0 for all n. Thus Taylor series of f in some small neighborhood is 0. But the original function is non-zero in any small neighborhood of f, which means that Taylor series does not converges uniformly to f in any open interval containing 0. Hence option D is also wrong. Okay. So we are done with the week 0 assignment. Thank you everyone.